Okay, so we're gonna continue today on the high-dimensional space, high-dimensional data visualization. Last time we heard about biplots, which is on the left-hand side, which is essentially a projection of the data in the PCA basis, principal component basis, where this is the first one, first principal component, the major one, and then is the secondary one. And you project everything into this data points and axes. And here on the other side is this more recent development called Subspace Voyager, which is essentially the data projected into 3D PCA basis, and you can rotate it if you like, right? I showed that last time. I think the only really difference is that the axes are plotted on the periphery, and the longer the axis, the projected dimension axis is, the more expressed that world is, right? So this is basically the same thing, right? So now what I want to show you next are some other visualization techniques that use this kind of, radial kind of display, okay, which is one of them is star coordinates. It's a pretty famous one. So star coordinates, basically there's no prior PCA analysis and there's no subsequent projection of the data into the spaces. Instead, what you do is you just take all these coordinate axes and lay them out in a star. There's like the first coordinate, the second, the third, and so on. These are all the different dimensions. Then a data point essentially is just really just take the value it has on the first coordinate, and then the value it has in the second coordinate, and just add that vector. Then the value it has on the third coordinate, and add that vector here. The value it has on a fourth coordinate, and add that vector here. And the value it has on a fifth coordinate, and add that vector. And so keep doing this until you arrive at the point here. So, and you just do this for all the points, and you get kind of this kind of layout here, okay? So basically this is the similar layout where just the dimensions is now plotted on the radius, just like in the Subspace Voyager, and essentially. What happens here basically is these points, they're not unique, right? They can be anywhere, right? So this point here could be generated by many different ways, right? There could be very high value in dimension 1, a small value in all the others, and then maybe another very high value in this direction, right? In the C4, in the C6. This is another way to get this point, right? So this is the location is not unique, which can lead to these ambiguities, right? Where 2 points may be close together, but they may not be close together in high dimensional space. They may be very different points, but they end up in the same place. That's a shortcoming of star coordinates. It's a simple technique, but it's a shortcoming that there's many ways in which a point can be reached, and which could basically create false neighborhoods, right? The 2 points may be close together, but they're really very different points. So what people then can do, you can allow people to change the axis, basically similar to this Subspace Voyager, which had a different interaction paradigm, but you can just change the axis, just grab onto the axis and move it around until you find like a constellation in which those points are nicely separated, and you can sort of watch as they move around, right? And then you can sort of find a layout where you think the points are really laid out correctly. And essentially what you come out, if you come out with a layout that may be very close to a biplot, or very close to a Subspace Voyager layout, right? By playing around with it. So there's really different ways you can arrive at such a plot, right? You can either biplot, or you can do with rotation along a trackball, or you can do a star coordinate layout and move the axis around, right? Many different ways to arrive at a similar plot, okay? Then another one is Radvis. That's very similar to star coordinates. The only thing it's really different that it normalizes into unit circle. That's the only really different, but it's very similar, right? You have these, you have these layouts, like here's one dimension, another, and the points are mapped in a similar way than here, okay? It's here, the mass spring layout is used, but it's very similar, okay? So it's just like, star coordinates and Radvis all these kind of techniques. Okay. Then a third one is called radar chart, which is actually a really nice one. So what the radar chart really is, it looks like kind of like a radar screen, right? So you have make these axes here. In this case, five axes, 1, 2, 3, 4, 5, right? And they're equidistantly spaced. And you really just, here 3 points are chosen. This is like point number 1, gymnast 1, execution, landing, style, creativity, and difficulty. This is kind of like a rating for a gymnast. This is gymnast 1. Gymnast 1 is the red one. Gymnast 2 is the blue one. Gymnast 3 is the green one. So the green one had a really good landing, and the second one had a really good execution, and the fourth one had the first one had a really good style. So you can really nicely compare the gymnasts. Obviously, the green gymnast was the best, right? He had a good landing and good creativity and good, not as good of an execution, but the difficulty was high, right? But the red one was really stylish, right? And this one had a really good execution. So radar charts are very nicely used, often used to really show 3 data points in high dimension. It kind of looks like a parallel coordinate plot, but it's radial, right? But you can sort of quickly see where some data points are better than others because the point is pulled out more, right? And then it's sort of a nice way to show, and it's sort of nicely sort of in a radial plot, so you can really see it like in one glance. You can see everything. Parallel coordinates, you have to go sort of from left to right, and here you can sort of see everything sort of in the focal display, right, where everything is around in the radial display. So radar charts are pretty well known and pretty often used. Okay. Then, so what's the commonalities of these, right? So all of these are essentially scatterplot displays or something like this. They allow the users to see the data points in the context of the variables, right? You saw this, right? Here's the variables and here's the points. Here are the variables and here are the points. Here's the variable, here are the points, and here's the points and the variables. Everything is basically points and variables at the same time, right? Points and attributes at the same time. That's what they all do nicely, right? But they can suffer from this projection ambiguity, right? Because you don't know, right? You have to really move the axis around to make sure that similar points are actually in similar place, right? And even then you can't be sure. Remember the biplot, right? Because you forget actually the third PCA vector, so there may be ambiguities if the third PCA vector is also very, very significant. Some points may project in the same place, but they're really not similar, right? So basically all of them suffer under this projection ambiguity. And some of them offer interaction to resolve some of these shortcomings, but this interaction can be tedious, okay? Because you have to move the axis around, you have to rotate the trackball, showed you some ways to optimize it, right? By using optimization, view optimization. We talked about that last time, so you can do that, right? So now I want to find out other visualization paradigms that can overcome these problems, right? That you don't need that much interaction, where things are sort of optimized and there's not so much ambiguity, right? So one of these is, algorithms that optimize the layout to preserve distance and similarity in high-dimensional space. And you learned about such an algorithm. It's called MDS, multidimensional scaling, right? It actually does that, right? It lays it out, tries to figure out a layout where the points are spaced in high-dimensional space and then also in low-dimensional space similarly, right? So because you optimized for that with a mass spring layout or with an optimization algorithm, okay? But what you can't do is you can't see the attributes in that space, right? You couldn't really see that, right? There was a multidimensional scaling. You're going to see the points together in a similar layout, or you could see the attributes all together in a similarity layout, but you could not see attributes and points at the same time. That's where these things really were good, right? Because you could see the points and the attributes, but they had ambiguities, right? So you can't really win anything, right? Here, like either you see the points in the neighborhood of the attributes, but you get ambiguities, or an MDS are nicely laid out, but you can only see either the points or the attributes, okay? So here's a display. I want to show you that does both, right? So here's a, this is a display that does both. So here is one that, this is the data-to-data similarity matrix, right? The one that you use in MDS to optimize the distances. This is basically a distance matrix of the data points, right? Distance matrix. This is M by M, right? You have M data points, so you get an M by M matrix to express the similarities of the data points, right? And then you get such a layout here, which is the traditional MDS layout. You can see these clusters nicely, right? So green and so on, right? And what is this? This is the VV. This is the variable layout, right? The attribute layout. This is n variables. You get an n by n matrix for n by n similarities. So here are the similarities of the attributes, okay? So the green one and the red, the black one are more similar, and not the green one and the blue one here is not so similar, right? That's why they're far apart, right? There's basically two MDS layouts. One is with the data to data, and the other one is with the attributes, right? But they're not together, they're separate, okay? So what can you do? You can essentially create two more submatrices, the data value and the value data. Really, this is just really this is basically the vectors of the data, right? There's M data points, and these are basically these are the vectors, right? These are the vectors, right? These are the data points, and these are the different values it has in the attributes, okay? And then you basically get an M by N matrix, M by N matrix. And this is really just a transpose, right? These are the data points and these are the vectors, right? It's the same thing, right? It's just a transpose. Now you basically put them all together and lay them out at the same time, lay them out simultaneously, lay out DD, DV, put them all together in a single matrix and lay them out with MDS, okay? And then you get the display like this, which is basically data attribute similarity matrix. This is the data attribute similarity matrix. Lay them out at the same time. Have to do some scaling, because the scaling is not quite right, so have to do some scaling to make them sure that they're all the same, at the same scale. And what you can now see, you can see these data points, the similarity of data points preserved, and you can also see the similarity of the attributes are preserved. And at the same time, there's also the points that are stronger in a certain attribute are located closely to this attribute. So these points here are more stronger in this green attribute, but they're also somewhat strong in the blue attribute. And they basically, this is all expressed in a single layout, okay? So to give you some example of this, how this works, right? There's a paper we wrote 4 years ago, like 4 years ago. So we call that the data context map, okay? And so let me show like this with an example, okay? So let's assume you have a data set where you have, I think I showed that last time, right? Where you have like attributes of a college. You have the academic attributes and you have the social attributes, right? So you have like tuition, score, PhD by faculty, academic value, and you have also the social attributes, like how good is the nightlife in this college town, how is the safety, how is the weather in that area, the dining, housing, and basically, and here are the colleges themselves. Here's Yale, Harvard, Berkeley, Pittsburgh, and Virginia Tech, and San Diego, and Columbia, right? So these are the colleges. And basically what I did here, I just took the data to data, basically how the colleges are related with one another in terms of the academic and social attributes. And here it is the values, and here is the variable. How are social attributes correlated with the, how is every one of those attributes correlated with the other, right? And now you can sort of see from here, it's basically a joint display, right? You see academic value is very closely related to PhD by faculty. I think we saw that in the previous slide set. Tuition is also related very closely, right? You pay more tuition when you have a school where you have a higher academic value, and the score in USU's report is higher. Then weather, somewhat related to safety. Weather is also related to dining, interestingly. Athletic is related to nightlife. So if you have a school that has a good athletic program, nightlife tends to be better. Transportation seems to be better. Population doesn't really matter much. It's not related to much. Here you can see the schools now are laid out in the same context. Right? Remember, now you can sort of see how the data points are related to the attributes. You can see MIT has a high tuition but good score. Harvard is here too, and they're also similar together, right? Yale is also similar together, and then here is University of Virginia, right? It's a little further away, has a really good athletic program. Texas A&M has a good location for some reason. Virginia Tech. So these schools have good athletic programs and good nightlife. Columbia is in New York City, is at a very high population, right? All the others are in little smaller towns than New York City. So that's why Columbia is closer. And that's where the rich people live. Like the Columbia is where the rich people live. Like New York City is where the rich people live. I'm not one of them, but nevertheless, so basically what this display gives you, it gives you similarity to data points, right, is laid out. It gives you similarity of the attributes, and it gives you the similarity of the data points to the attributes. How are the data points attracted to the attributes, right? You see, if they're closer to an attribute, then that means they have a higher values in those aspects, right? So this is good, but the problem is because you took this high-dimensional space, which is not necessarily a two-dimensional slice, right? It's high-dimensional, and you try to squeeze it into the two-dimensional display. And we learned this before, right? This is just very hard to do, almost impossible actually to do, in a general sense. In a general sense, it's impossible to do. So what you need is really more than that. You need basically some interaction, okay? And I'll show you what we can do here, right? So let's have these sliders on the right-hand side, okay? Where these sliders allow the user to select certain boundaries, okay? For example, user can say, well, my academic value should be higher than a certain minimum, right? So I could take that slider really further out. Or I can say athletic value. I want to go to a school that has a little bit a higher athletic value according to that college proper data set. Or I can take a school, I really can't pay so much tuition, so I can only go lower, right? And so on and so on and so on. Maybe nightlife, whatever I can. I can basically take these sliders, and let's take one of those sliders and see what happens. Okay, let's take one of those sliders and see what happens. So let's see tuition. Okay, let's take the tuition slider and see what happens. Okay, so now what you can see, as I move the tuition slider down, as I take the tuition slider down, I'm starting to exclude certain schools because those are all the schools that are more expensive than the value I've chosen here. Okay, and the ones that are still in this green region are the ones that fall within the low bound, the lowest tuition that you can ever pay, and the one I have chosen, right? So these are the inclusion. And as you can see, this region is very curvy, right? This region isn't like round or circular, right? It's sort of curved like this because the high-dimensional space was mapped into this two-dimensional space, right? There's a distortion happening. So basically what used to be a hypersphere, is now essentially a sort of an irregular region in the two-dimensional projection, okay? And actually, turns out it had projected in two separate regions. And this is really the interesting part about high-dimensional space. But if you take a hypersphere in high-dimensional space and try to preserve that hypersphere in the two-dimensional layout, which is optimized for this in this dual way, right? Where attributes are laid out in a way that they are optimal in the spacing, and also the data optimized, and also the relationship of data points to the attribute vectors is optimized. If you take all this and try to warp as much as possible, take that high-dimensional space and warp it into this two-dimensional plane, what you're going to see is that these boundaries also warp like this, okay? And that's basically a really good demonstration of this high-dimensional space, how it really gets interpreted in two-dimensional space, right? So now basically what we found out is these schools that are affordable, okay, and the ones that are not affordable outside. So let's go further and say, okay, what happens if I take like my academic score, right? You know, let's see which schools actually, you know, fulfill my academic criteria, right? So now I'm gonna go down, right? I'm gonna lower my academic, I'm gonna raise my academic value, right? The threshold I wanna be at. Sorry. So, you know. So now basically I have said, okay, I want the tuition to be here. I don't want to be like, I don't know, 10K, 10,000 or something like this. And the academic value, I don't really want to be all the way on the bottom. I want to be like to a school that's somewhat okay academically, right? So, or actually excellent too, right? So Yale, MIT, Harvard, they're all in that, right? Because they're all beyond this minimum value I chose. University of Virginia is also here. Okay, you know, so turns out the University of Virginia is really good, right? It actually turns out to be both affordable and good athletic score, right? Sorry, and good academic score. So wow, you know, that's pretty good. But let's see, you know, I still have this other constraint. I want to go to a school that has a really good athletic program, so I'm going to like go on more, right? So let's go further and say, okay, athletic. Okay, let's go to athletic, and then use this athletic slider, okay, and then make a region there, right? And I'm gonna increase my expectation athletic. And now I learn, right? So these are the schools with good athletic programs. I can also see here, those really good schools like MIT, Harvard, Yale, they don't really fit my academic standard at all, right? They don't really have good academic programs. It's true, right? Yale doesn't really have a good football team, and neither does Harvard or UC Berkeley. But you know, but University of Pittsburgh has, and then USC has in some ways, and definitely University of Virginia, right? So here I see, you know, these schools, the University of Virginia actually has everything, right? It has a good athletic program. It's in this region. It has a good tuition, right? It's in the region, in the yellow one, in the green one, and it has satisfactory academics. Okay, it's in the purple one, right? So just by using this interaction, right, that I showed you, where you have sliders and then try to visualize the distortion of the high-dimensional space in the two-dimensional plane, you can get some insight into your data with playful interactions. Right? I can move these sliders anywhere I like, and like now I can add weather, I can add transportation, add more and more of these regions, and eventually find out which school I really like and which ones I don't. Right? So, you know, so this is basically sort of a really good demonstration of how can I sort of bring everything together in a single display: attribute similarity, data similarity, figure out which areas in high dimensional space are interesting to me, right, by doing these sliders. So it's sort of like a, you know, a good sort of good visualization paradigm. Okay, I just want to like demonstrate that, right? So, okay, how's the initial position, okay, of the red attributes determined? Okay, good question. Okay, the red attributes. Let's go back here. Basically, all these positions are determined in the same way with multidimensional scaling. Okay, so there's different schedules I can use, and we experimented when we did this paper. We experiment with different ways. You can first lay out the attributes, which are the red points, right? I can do MDS on the red points first, okay, and then freeze them, and then do another layout of the blue points, but respecting the layout that already have been in the red points. Or I can lay out everything at once, or I can lay out everything a little bit and then keep adjusting it, right? So eventually everything is sort of laid out at the same time, right? So because I took this matrix, which used to be just a data similarity matrix and just a variable similarity matrix, which are the red points. These are the blue points, and these are the red points, and added these vectors here, which is just the data vectors, put them together and created this big matrix, and just use MDS on that, right? Just try to preserve all of those different, you know, similarities, right? And then that's what I did. can we have different shades of colors depending on the intensity of the attributes when we. So we haven't done this. That's a good question. Where's the video? Okay. Yeah, well, it's basically we could do that, right? So we have like some interpretation which we haven't published yet, where you can have iso contours, right? So this is basically, where this is this could iso contours, right? This is like the $10,000 contour. Sorry, this is the $10,000 contour, and this may be the $8,000 contour, and this is the $6,000 contour, and this is the $12,000 contour. So we have like this sort of topographical map. You could also use different shades, right? Where you have this, where you could have very intense green in the smallest amount in the most affordable schools, and then you sort of go out. You can have very intense purple in the middle and then fall out like this. We haven't done this. A good idea. We haven't done this. We went with the iso contour. I don't have this picture here, but we've done that. Create sort of a geographical, topographical map like they have on like for mountains, right? So we did that. But so far, it's really just using the sliders. Basically, just using the sliders to figure out what these contours are, right? You can just take the sliders and move them down, and you sort of imagine the contours as they happen, right? But we could plot a contour here, another contour here, another contour here, and then then you would remember what these boundaries were, right? They could do that, but we haven't done that here in this particular application. But it's something we have actually implemented, but we haven't published that yet. So okay, hope that explained it. So now let's go back to the scatterplot matrix. Okay, you guys all have done scatterplot matrix in the lab assignment, right? Lab 2. So this is like a single bivariate scatterplot, and this is the scatterplot matrix, right? Like this is basically attribute 1 versus attribute, so attribute 1 versus attribute 1, attribute 1 versus attribute 2, attribute 1 versus attribute 3, attribute 1 versus attribute 4, right? And then you basically go do this. If you have n attributes, you can build an n-square scatterplot matrix, okay? And these are all just transposed, right? They're always the same, right? They're just rotated, okay? So because this is the, 1 to 4 and this 4 to 1, right? Attribute 1 versus 4 and this attribute 4 versus 1, right? It's the same thing, just flipped over. Okay, so let's assume you have more, scatterplot matrix of like, let's say, this is like 5 by 5, okay, but there could be ones, essentially, you basically have, tiles like, if you have depending on how many variables you have, you get n square tiles, right? N square tiles. And you're just going to have really quickly, you're going to have like lots of tiles. Let's say you have like 50 dimensions, you're going to have a 50-dimensional scatterplot matrix, right? 50 by 50 tiles, which is really hard to see, right? So what can you do, right? So basically, if you have this very large scatterplot matrix where you have 50 by 50 tiles or more than that, right? Which is impossible to show, right? In your case, in your lab assignment, you chose you use the most prominent dimensions determined by the PCA factor loadings, right? You use that kind of way to figure out what the most interesting attributes were. But maybe there may be just interesting scatterplots that you could see, right? Don't worry about like, what the attributes were. Maybe they're just interesting distributions depending on whatever the pair is, right? There could be attribute 5 and attribute 55 that have very interesting relations together, right? Which have correlations, But sometimes correlations is not strong enough, right? When you have a correlation, this has a heavy correlation, this has a strong correlation, but maybe this is not so strong, but maybe this is interesting. Or maybe there's two clusters, right? For example, here, where you have this kind of scatterplot here on the left-hand side, right? Where you have 3 clusters and they're nicely separated, right? They're not really correlation or anything. There's no correlation that you can use to select that one, right? It's only interesting because the three classes nicely separate, and there's like these two attributes that make it happen, right? You know, two attributes that make it happen. And there could be, you know, many, you know, if you have 50 attributes, there's 50 square scatter plots, and some of them could be have interesting class relationships and some of them don't, right? For example, this one is interesting and this is a pair that's not interesting, right? This is like an attribute pair where, you know, all the three classes are intermixed. So there's really no value in looking at this, right? Because, you know, there's nothing to be learned from that plot, right? And it's just that it's random, but that's not really that interesting, right? This is more interesting. You can really see some classes, for example, marketing, right? You could see these are the rich customers and these are the poor customers, these are medium customers. You can sort of learn, you know, about how they behave in terms of these attributes, right? That helps you in figuring out some strategy. Here, they're just randomized, randomly distributed, right? There's nothing to be learned from that, right? So the million-dollar question really is, how can I, let's see, I have 50 by 50, you know, scatter plots, thousands of scatter plots. How can I, from all these scatter plots, how can I determine the ones that are interesting and the ones that are not? Okay, so you need some machine intelligence. Okay, so a metric that can determine a metric that can determine if a scatter plot is interesting or that plot is not interesting. For example, one of them is this DSC, which is the distance consistency metric. Okay, DSC by Sips et al. Okay, DSC basically is a very good metric, and these metrics have been studied for a long time. Okay, so there's lots of metrics that try to determine which scatter plot is interesting, where things are nicely separated, or some other metric but it always boils down to some sort of separation metric, right? Turns out there's lots of these metrics, and I'm going to show you another one on the next slide. But this DSC metric has really been found to be a really good one. Okay, a really good one. It actually really, in all these comparison studies, this DSC metric comes out pretty high usually. Okay, so you know, so let's talk a little bit about how it works. Okay, so basically the way it works is this formula here. Let me explain it to you. So basically, what you do, you know, you determine if a scatter plot is good. A scatter plot is good if a point here, let's say you have the cluster center for each of these clusters, right? So you have the cluster center of the red cluster of the blue cluster, and a cluster center of the green cluster. Same thing you can compute here. You can compute a cluster center for red, green, and blue. Of course, these two cluster centers are very close together because the red, green, and blue clusters are really overlapping. Right here, they're nicely separate, right? And then you compute this metric here. You basically say if every point in the point cloud, you ask, is this point closer to the center of its cluster, or is it closer to the center of another cluster? If it's closer to the center of its own cluster, then I call that true and I give it a point. I increment the counter. Okay, and if it's not closer, then I don't count, right? Then I don't count it. Okay. So if I have this situation, then all these points here are probably closer to the red cluster center than to any other center. And the green points are closer to the green cluster center to any other center, and the blue points are closer to the blue cluster center than any other, right? So this is going to have a very high distance consistency metric, okay? So they're all going to be true divided by k, which is the number of points, okay? They're going to be close to 1. Okay, this is just normalization, or close to 100. So this here is obviously, this is 90, and this one here, this is really miserable, right? Because some points are close to their own cluster, some points are close to the other one, right? To the cluster center. So this has a really not a good metric, 49 point, right? Same thing here. This has 29, this has 15, this has 99, this has 74, right? 99 is clear, right? Every point in the red one is probably close to the red one and blue one. Everyone here on this side is probably closer to the blue clusters center than to any other center, right? So then basically now you can just go do this, right? You can just go take all your scatter plots and rate them with this DSC metric and rank them by the value they get, right? and you just like show the top 10, right, to the user, right? You basically show this one and then show another one that's really good, another one, and don't show this one to, this may be at the, this may be at the, rank 55, right? That you will not show that, right? And the user will first see those really clean ones, and it will be like a ranked list, basically, where the good ones are shown first and the bad ones are shown later, right? And then you can just say, the user may say, show me the 20 best bivariate, show me the 20 best bivariate relationships, okay? And then you're gonna run this distance consistency metric, and you're gonna show the 20 best plots, right? And then user can learn from that, right? Because bivariate clusters are really easy to understand, and then you show the best bivariate clusters you can give, right? So that's like basically here, right? You would show this one. Well, here there's no bivariate cluster, there's no classes, right? For this to work, you need classes, okay? So this is a really good way for automated scatterplot selection, okay? Another one is this one, done index is a nice one too. It's a similar idea, right? So it computes these two metrics here, okay, where Ci and Cj are two centers of two clusters, like the cluster I and the cluster J, okay? And you try to you basically look at all the clusters separately, and you find out which two clusters have the minimum distance, and then you write that here, okay? So you look through all the different pairs of clusters, and whatever the minimum difference is, here, for example, this is smaller, this center here, these two centers are closer together than these two centers here, or these two centers here, right? So the minimum Ci, Cj would be this minimum, right? And then at the same time, you look for the maximum intra-cluster, like you try to find out how far apart points are within a cluster. Like that's what's expressed here. Basically, for each cluster, you compute this metric here, like the distance of a point to its center, okay? And you sum it all up, right? And you divide it by the number of points in the cluster. And this is going to be higher if the points are more spread out, right? And it's going to be smaller when the points are close together. So I'll give you like an example. So the done index here is pretty high, right? Because the intra-cluster distance, like the points within a cluster, is much tighter, right? Although the centers are pretty far apart, and the points inside within each cluster are pretty tight, right? And here, points within a cluster are pretty far apart. At the same time, the centers are also closer together, right? So this is going to have a low done index, and this is going to be a high done index, right? So that's another good way. So you could use it for k-means clustering, for example. You can compute the done index for k-means clustering, and figure out, well, if the k-means clustering, if the done index is not very high, then you have to choose more centers, right? Or maybe you have to run the k-means clustering again, right? So it's another, you can compute the screenplot again, right? So it's another way to figure out which scatterplot is good and which scatterplot is not so good, right? So that's just, this is another distance, right? Done index is also very popular, right? So DSC is popular, done index is also popular. There's a lot more, but I want to show you the ones that are really popular, so you have a little bit of an idea of what people do, right? So it's a pretty good way to determine the quality of a clustering, or determine the quality of a scatterplot, and how isolated these clusters are. This can matter a lot of times, right? Oftentimes you want to know, is there concrete populations that are separate from one another, or is it really something that's sort of hard to see, right? Here, maybe a human is not needed, right? A human can just, the machine can figure out, what the clusters are. Here, a human is needed, right? So you could basically have an interface where you show the human only those clusters that have a bad done index, right? And so the human can say, okay, I think this is a cluster and this is a cluster. And here a machine can label it easily, right? The machine can say, oh, this is probably cluster 1 here and this cluster 2 here, done, right? The human does not need it. But here, for this, the human is needed. A human says, oh, wow, there must be a cluster here, because the machine can figure it out, but the human can figure it out, right? So you can use the done index to share the load between a human and the computer, right? Give the human the hard ones, and the machine can do the easy ones, right? The easy ones are the ones with a high down index, and then the you know, and the yeah, and then right, the low down index, and the human does the other one, right? So the machine does the high down index, and the human does the low down index. Okay, so last one I want to talk about is diagnostics. It's also a pretty famous algorithm for cluster for scatterplot visualization. Okay, so here basically the idea is to describe the scatterplot with features, and then sort of classify the scatterplots by human readable features, by human readable attributes. Okay, you say like, okay, like outlying, skewed, clumpy, convex, skinny, striated, stringy, straight, monotonic, right? These are sort of human interpretable labels for scatterplots, right? So this, for example, what this is here, like look, the red one, the red colors mean strong, skinny. So this is a really stringy kind of thing, right? This is another stringy kind of look. And you can compute these metrics with a graph algorithm, right? There's a minimum spanning tree that you compute, and then you can interpret that, you know, in different ways. There's like different metrics described on those spanning trees. You know, if the spanning tree is bushy or not, then you can sort of figure, you can rate, you can then if it's not bushy, then it must be a stringy one, and so on, right? And like same thing with skewed and so on, right? So you can build a minimum spanning tree on these scatterplots, and depending on metrics that you compute on top of the minimum spanning tree, you can categorize, you can basically give values for all of these different metrics, right? So this is the one that's really skinny. That's another one is skinny. Then another one is skewed. This is pretty skewed, right? Look at these sort of outlying kind of things here. This one is not skewed at all, right? There's like a clumpy thing here and some ring around it. This is another skewed one, right? There's lots of things on the periphery. Then convex. This is a very convex one, and you know, and then skinny we talked about, and straight. This very straight, right? It's kind of a monotonic relationship here, you know. So basically, it's sort of, so the human may say, you know, give me like all the distributions that are clumpy, okay? Then basically you're going to see like sort of clustered kind of things, right? Where there's like clustered. Or give me all the scatterplots that are really, really, you know, skewed, because the skewed ones are like the ones where there could be, you know, some outliers that maybe that I want to clean up, or they want to, like, you know, maybe that's interesting to me in the data analysis stage, right? So, and then I can even make another, you know, the plot of plots, basically, right? The scatterplot of scatterplots, where I can basically make a scatterplot matrix based on the ratings each of these scatterplots have, right? So each scatterplot essentially is now a point here, right? This is like the, you know, these are like the dimensions that I showed here, right? Outlying, skewed. They built these dimensions in a scatterplot matrix. And then each point basically is a scatterplot now, because I rated each scatterplot in terms of these metrics. Then I can, you know, so I can basically now look how my scatterplots overall, what is my distribution of scatterplots overall? Do I have lots of skewed scatterplots? Do I have lots of skinny ones? You know, things like this, right? So you can basically visualize the scatterplots in an abstracted way, right? So that's basically scatterplot that does diagnostics, right? This by you know, Tukey came up with this, right? Tukey, famous statistician, he mentioned that in one of informal papers, you know, he mentioned this, and then Lee Wilkinson wrote a paper about this. Okay, so that about diagnostics. This became really famous. So there's lots of uses for diagnostics, but that's why I want to introduce it to you. You know, it's basically diagnostics of scatterplots, right? That's why it's called diagnostics, scatterplot diagnostics. And you can diagnose the scatterplots, represent them in terms of these human readable attributes, and here's a spanning tree of one particular scatter plot here, right? And then sort of reason about them, right, and categorize them. Okay, so that sort of ends my lecture for. That ends my. Is there a key for color? Yes, red means high and blue means low. I should have made to put the color. I'll put the color legend next time. I always, red means high. There's a lot of outline here, and there's not a lot of outline here. So red means high, whatever that is, and blue means low, whatever that is, right? And green is in the middle. Okay, so it's basically like a heat map, basically. Remember, like heat maps, rainbow color map is not good, but here they used it. Okay, so that's basically what that is. So okay, so this sort of ends my lecture on high-dimensional data visualization. So we learned lots of things, right, about like how to do this, and I should put the summary here. So I'll add a summary at the end after I publish the slides. So are there any questions about any of this high-dimensional data visualization and how different things, metrics on top of them, right, and then talked about MDS, star coordinates, bivariate, and then this was what we did last time, biplots, ambiguities, correlation, parallel coordinates, and how the high-dimensional space, like what is going on, right? So really look at this, right? It's a pretty important area in data science, right? And understanding high-dimensional spaces is really important, right? So it's good to know how this works, right? And what are the trade-offs? There's no perfect high-dimensional data visualization technique. There's ones that work better in one way, ones that work better for another, right? So you have to pick your poison, but anyway. Okay, so if there's no question, then let's go and talk about another very interesting topic called interaction, right? Let's talk about interaction. So interaction is really needed because we saw in high-dimensional data visualization already that interaction was really a good thing to do to navigate the space, right? To navigate the information and really show what you want to see. Okay, so an example here is this, right? Principles of interaction. So basically, when you have lots of data, right? This is a tree map. We'll talk about tree maps later. There's a parallel coordinate display. This is a scatter plot. When you have a lot of data, oftentimes you see the forest for the trees, or can't see the forest for the trees, or the other way around, right? So you can't really. Sometimes you want to see the overall structure, but then you can't really see individual things. Sometimes you want to see individual things, but then you lose what really happened in the big scale, right? So it's always this trade-off, right? So this is really, interaction can really help here. Okay, so here, like these internet routes is overwhelming, right? You can't really, really see, it looks really impressive, right? Looks also very impressive here, looks very, the parallel coordinate display is just this black, there's too many points here, right? You can't really see anything anymore because too many points. There's too many points here, right? Looks impressive, so if you want to impress someone, right, you can show them this picture. But if you really want to learn something from this, not really, right? So that's why this is in New York Museum in the MoMA, right? In the Museum of Modern Art, right? Because it looks like art, but does it look very insightful? You can see some hubs here, right? But what are they, right? So so interaction is basically the way a way to allow users to control what is currently shown, right? You want to basically see the level of detail, extent of the data, and the aspects, right? Extent is basically spatial and value, and the aspects are the attributes. Remember, we saw that before in a data context map, right? We showed the attributes, but we showed the data at the same time. And there was not a lot of detail. There was not a lot of data in this display, right? Because we had not a lot of data shown. But at the same time, if we allow the user to control what is currently shown, you don't want to lose the user, right? You don't want to like show me individual trees, but don't let them see how to get out of the forest, right? Or how to see other trees in the forest, right? So you have to give some navigation hints, right? You have to really allow the user to navigate the forest to see different parts of it, but still let the user see individual trees, okay? So two powerful paradigms are there, right? Overview and detail on demand. This is based on the forest and the trees. The forest is the overview and the trees are the detail. All focus on context, which is the trees is the focus and the forest is the context. Okay, so basically there are two powerful paradigms that sort of let you do this at the same time, right? Let you see the forest and the trees at the same time. But this is basically achieved by interaction, right? Where you can quickly go from overview in detail and back, right? And because you need to control it and you need to show it in a continuous way, right? You don't want to like quickly go from one to the other, because then you lose the person completely, right? You all of a sudden you show the detail, but where did it come from, right? So, or all of a sudden you snap back to the overview, where was the detail, right? Where did it come from, right? So you don't really know that, right? So you really need something, and that's the interactive, right? It has to be responsive. You can't have something that takes for a long time to get to the next stage, right? Something has to be, just like in real life, things have to happen quickly and immediately. Otherwise, you lose your train of thought and you don't know anymore what happened, right? So it has to be real time or near real time, okay? Quick visual feedback is key. So put the human in the U, basically. Appeals to human expertise and intuition. Then you need a good human-computer interface. And then remember what we talked about, color perception, right? Remember all this. Those are the rules to build a good human-computer interface. And interaction basically can help make sense, put things in proper context, deal with data overload, and tell stories with data, right? Like really allow you, who has already navigated the data, now navigate the data for others to explain what you found, right? And show them the same story that you have slowly developed, right? By interacting with the data and really try to like navigate the forest with someone, you know, along with you on the ride, right? A passenger that you can take along on the stories you're telling, and then do this interactively, right? Because you already know the route, right? So you can just replicate it again, right? So how do you know if something worked or not? Okay, well, you have to do human subject studies, right? You have to do user studies, right? Because humans are supposed to be consumers, so you have to, you know, do user studies. And we're going to have a whole lecture on this, how to do good user studies, okay? User study, very important, okay? Let me give you some techniques, okay? This is from the Few book. Visualize this. The Few book, Stephen Few's book. So basically, these are these different interactions that you have, that you want to support, right? Compare is a really important one, right? That users compare. Then sorting is one. Users should be able to add variables. Users should be able to rescale, so things are more better comparable. Pre-express, sometimes you have to show it a different way to make it more easily comparable. Then filter is like where you control the detail. Highlight, where you emphasize certain aspects in the forest. Annotate, where you start labeling things. You know, bookmark, where you remember things. Aggregate, where you put different things together in a single view so you can compare it better. Revisualize. Zoom and pan, where you zoom in and pan across. Details on demand, right? Where you basically have an overview and then you zoom in, right? So these are all these different sort of interaction techniques that you have used, that people have used. So I want to like show you a little bit some of these, so you see a little bit on a simple example how these interaction techniques work in a very simple way. Okay, so let's assume you have been offered a car to buy, right? So there's this car, you know, you don't know anything about cars, let's assume, you know, and this car you found in a newspaper, right? And or some friend has offered to you, you know, and then you tell it, okay, this car has, the friend tells you, or the stranger that you meet somewhere on a used car lot tells you, okay, this car has 60 horsepower, weighs 1,834 kilograms, you know, and has and the acceleration is 8 seconds. It takes 8 seconds to go to 60 miles an hour, right? And he tells you this is the best car you have ever seen. He tells you, right, that this is like the, buy this car because there's no better car than this, right? Look at it. It has 60 horsepower, 1834 kilograms, 8 seconds. How can you find any better car? And you say, wow, you know what? I have this car, but how do I know if it's the best car? Okay, so, how do I know? So what does this mean? 60 horsepower, right? What does it really mean? This is my car, 60 horsepower, great. But now what you need is something to compare, right? You need all the other, you need to see all the cars that guy has on the lot, right? All the cars that are available for sale in a large magazine, or all the cars that are around on the market, right? So this is the 60 horsepower, and quickly you learn, wow, there's cars that have a lot more horsepower than this car. So whatever this guy told me, 60 horsepower is actually really low. There's almost no car that has lower than that, right? So now you learn something about cars, right? You see, wow, 240, wow, this is a lot. This is actually not a really good car in terms of horsepower. He told me it was really good, made this big bar, right? And say, wow, this is a huge bar, but really, once you compare it, but it's really hard to see how bad 60 horsepower really is, right? Like, where is it? Like, how many cars have 60 horsepower? How many cars have less? How many have more? So what you need is sort, right? So you need to sort. So here's your car, and now you can easily see it's at the tail, right? Very low, in the low end, right? There's cars here. Turns out, there's a steep change here. So this is really not a lot of cars have very high horsepower. This sort of seems to be a nice, there's like a similar slope here. So this seems to be like the sort of range where cars start to improve. And here this seems to be like extreme improvement, right? Luxury cars, there's like a plateau. And here, this sort of lower, right? There's like steep decline, right? And here's my car, right? So this is really, now you can tell the guy and say, okay, this is a pretty slow car. What does this, the terrible car, right? And then, then you may want to know, like, how is it correlated to weight? Because he told me it has like this 1834 kilogram. How is it correlated to weight? Okay, so now you put the weight in there too, right? So now here's my horsepower, really low, and here's my weight up here. So it's really hard to compare, right? Hard to see, right? Because this is like teeny weeny small, this is really big, because the variables, the values are very different, right? The weight is a big number, and the horsepower is a small number, right? That's why it can't be plotted in the same scale. So what you can do, you can rescale it, right? So you can like basically make them comparable. Use a different scale for the horsepower than for the weight, right? So now you can really see, okay, wow, clearly I can see now that weight is correlated to horsepower, right? So the more horsepower the car has, the more weight, the more heavier the car is, right? So a teeny weeny small car, has low horsepower, and these heavy things on the far end on my lot, the lot has much higher horsepower, right? So I can only look at the cars, right? The bigger they look, the more horsepower they probably have, right? So whenever the guy shows me a big car, I can say, this is a more powerful car than this small car this small teeny weeny car on the left hand side, right? So now, how does it relate to acceleration, right? You want to know, how is this horsepower really? Is this car, really good in terms of acceleration, right? I have a certain horsepower, and the guy told me about the acceleration, 8 seconds. How is this really relating? Is this car really slow in terms of the horsepower it offers, or is it really high in terms of the horsepower it offers, right? So I plot this, but you can see here it's non-intuitive, because it actually slopes down for the higher the accelerations actually go down as the horsepower goes up, right? These are like similar cars. This is car number 103, has low acceleration, high horsepower. So I have to re-express it, right? I have to say acceleration should really be 1 over acceleration, right? should be measured in 1/second, 1/second, right, and not seconds. Now they're more comparable, right, because now the acceleration goes up as the horsepower goes up, right? I get more, per second. I get more miles per second than with higher horsepower, right? So now it's comparable, right? And I can see there's a clear relation. Wow, this car here, has a really good acceleration, doesn't have a lot of horsepower, but here's a really extreme, must be a light car or something like this, right? So basically, these are all interactions I would run, right? Starting from here, from this single car, I put them together, then I sort them, then I compare them, and then I rescale it, right? And then re-express it. And I slowly have these interactions, basically just a button that would do this for me, right? These are interaction techniques, okay? And there's others that I'm going to tell you now about. So, for example, another one is this level of detail, filtering, right? So here's filtering. So look at these groups here, right? So there is all of it at the same time, right? So by filtering, I can basically now say, this is like a connected graph, right? I filter now, I say, give me only the top 200, the top 750 connected nodes. Give me only the nodes that have the highest connectivity, and 750 of the top 750 in terms of connectivity. So basically only give me the hubs. And here I see every node, even the leaf nodes, and here I only see the hubs, right? So now I can already see some structure, right? Before, just a hairball, right? And here I can see some structures. Now give me 350 top connected nodes, right? So I can now really clearly see the hubs, right? Before, sort of see, but there's still a little bit, some lower key nodes that are occluding it, right? And now I can really see, wow, this is really the hub. Here's another hub. Here's another hub, right? And these are like sort of the hubs of the hub, right? So, by filtering, just analyzing the connectivity per node, keep a matrix of this and just only plot the ones with the high connectivity or the high, the high outgoing links, then give me that, right? So this is filtering, just filtering on the connectivity of the nodes. Zooming, this is zooming, where I zoom now into certain neighborhoods, right? Here I filtered, and now I'm zooming into a certain neighborhood, like just zoom into one of those hubs, right? This is the Saab neighborhood, for example. The cars that are related to Saab, right? Or the concepts that are related to the Saab car. Okay, this is the graph of concepts. Okay, concepts, and the zoomings are more, right? So just keep very, very zooming now helps, enables me to zoom into certain aspects and analyze it in a local neighborhood, and then I can zoom out and go back out here, right? And back out here, right? And back out here, and back out here. So basically, zoom and filter, right? Zoom and filter, and do this interactively. And then I can go back here, right? And zoom into a different node and look at that one, right? And back and forth, right? So an interface needs to support that, right? An interactive interface needs to support this filtering and zooming. So you can really quickly go into certain aspects of your very high, very complex data set and look at particular aspects of it, okay? So that's very important. And this one is aggregate. So here we aggregated, biplot is a typical aggregation, different clusters in terms of the basis, right? Here aggregated certain clusters that like certain higher level clusters into points. Here aggregated parallel coordinates are aggregated, different attributes in a single plot, right? Aggregation basically is when you take the data and put them in a single display. That's good for overview, right? And I told you before, what I usually do when I analyze data, first I make a correlation plot to look at all the attributes, or make a biplot to just see what is out there, right? How are the attributes connected? How there are natural clusters there? I oftentimes look at a parallel coordinate display, optimize it with correlation ordering, just to see what's going on, right? Like, what is my data all about, right? Is there anything interesting on a higher level? And then I go zoom in, right? That's what I usually do when I look at data, right? So a very important paradigm is this overview in detail, okay? Overview in detail. This was invented by by a person named Ben Schneiderman, who is actually a graduate, is the first PhD graduate of Stony Brook University, you know. So he's a very famous guy. He's now a professor, just retired, I think, University of Maryland, College Park. He's one of the fathers of information visualization. And he came up with this, what's called the visual information seeking mantra, also called the Schneiderman mantra. So, you know, that's a nice piece of trivia to know. So basically, it really is very central to many visual design guidelines, right? So this information, this overview, zoom and filter, detail on demand, right? And keep doing this, right? Overview first, then zoom and filter, what I showed you before, right? Zoom and filter, and then show the details, right? First zoom and filter, and then show those details that the user has demanded, right? And then keep doing this, right? Keep doing, zoom out, overview, zoom, do another one. So basically, this is repeated because this is something you keep doing, right? You keep doing all the time. You keep overviewing it, zoom and filter somewhere else, show the details, and overview it, zoom and filter, detail on demand somewhere else, right? You keep doing this until you learn about the data, right? First, you look at everything, the gestalt of the data, and then you keep looking at the details. What does it look like in local neighborhoods, right? Just like visual search does, right? When you enter a new room or enter something new, that's how you always do this, right? You look at the scene, first you sort of do like look around what is there, and then you look at particular key parts, right? You may look, oh wow, there's a lot of people in this party, and then you look at a few of them that you know, right? You look for friends that you know, or you look for interesting people that you want to meet, right? Or you look at the desk, right? There's a lot of stuff on a desk. Then you first overview it, and then you look at particular parts of the desk, right? You know, or a picture, right? This is visual search, the concept of visual search, right? It's the visual search. Or first you look at everything, draw a mental map of it, and then you look at details, right? That's basically how it works, right? And this just the whole visual search that humans do by design, right? Like everyone does this, you know, just try to implement that into an interactive interface, right? To replicate that, because it works so well on humans, because humans have done this for thousands of years or longer, 10,000 years. Now you try to replicate that kind of thing in an interactive visual interface, right? Overview, zoom and filter, details of demand, right? So here's some examples of this, you know. So here's the overview, and here's the detail on demand. Here's the overview, here's the detail on demand, right? So it's basically indicated with this fan structure. This is a histology slide, and these are like individual cells, right? And this is the map, and this is an individual detail of this map, right? And you indicate it either with just pointing at it or with a fan, right? So detail is there, and you can move this fan around, right? You can say, look me somewhere else, and then you're gonna see like small zoomed in regions everywhere you go, right? Let's just imagine you move this point here, you move it around, and then it shows you a detail from another place, right? You know, maintains some context. Okay, another one is the problem with the overview and detail, the way at least the one I showed you, is that, you know, you have to basically shift the focus of attention all the time, right? Either you look at the overview here, or you look at the detail, right? You basically have to build this bridge all the time. Okay, so you know, so this is not bad, right? But it's you know, it's something that comes with it, right? So another one that you do is basically focus in context, right? This is where you don't have to do this. Okay, where you look at a single view and show the information in particular context, right? And that, you know, you maintain the continuity across the display. So it's basically the view shows the context. And basically, this is essentially what the lens does, right? The focus and context paradigm is a lens, right? There's basically the lens is embedded into the visualization, right? Instead of, it's not outside, separate from the visualization, it's now embedded into the visualization, right? And there's like this boundary, you know, where you can't see, you know, basically, you know, this is a particular lens where it's really over, basically it's hiding this part here because it's superseding, you know. So this is another lens that doesn't hide it, right? It's like high detail here, And then there's this region here where it's compressed, and then there's the regular region. So this doesn't hide anything, right? It just compresses it, but doesn't hide it. Here, it's hidden by this overlapping lens. And here it's just, you know, basically there's no frame to this lens, right? The lens is just frameless, basically, you know. So there's basically high detail here, and you don't have to show the grid, but you know, I'm just showing it so you can appreciate the distortion, right? So this is a fisheye lens, basically. This is basically a fisheye lens in some way, right? Fisheye lens does exactly this, right? It's like shows regions that are interesting in the focus of the lens at high detail, then it falls off, where you can't really read it really well because it's sort of compressed and distorted. And then out here, it's the regular level of detail, right? So here's this compression region, because you magnify it here, somehow you have to buy yourself this space, right? Because you magnify it out here, you have to make that smaller, so because you borrow the place from here, right? And then here it's okay, right? Same thing here, right? So the bifocal lens is essentially something like this, right? So it's just a metaphor, right? Basically, you take lenses are oftentimes, for like computer-based lenses, oftentimes basically implementations of things you know in neural nature, right? So you can always go and take a band like this, you know, like a sheet like this, put it on these two rollers, and look at it from the front, right? Basically, where it looks like this, like think about you're looking here in front, these are like slightly off, right? So you can see them too. So you see this in high detail, and then this kind of stuff falls off, like it's distorted, right? Because this is like just a small angle, right? It's like distorted. So this and then you can move this around, right? You can like a towel, you can move it back and forth, and then you can see this in high detail, and the rest you can sort of see it, but not at high detail. Okay. London subway map is another one of these displays. You know, you can sort of see this in high detail, and then the rest here is shown in low detail, right? You can just see the individual lines, but you can't see the labels. And here's a paper that we wrote a while ago. That's a volumetric lens. Okay, like think about it as a three-dimensional area. So this defines this whole concept of lens, right? This is the magnet. So basically, you build a focal point here, and all the rays basically go into this focal point, which essentially leads to magnification of this area here. So this area here is perspectively mapped out here to this area, so it appears larger, right? Because there's a perspective lens here. Then out here, there's no distortion at all, and here there's this transition region where the lens is actually the other way around, right? Where this is narrower than this, right? So now this gets compressed, right? This gets compressed. So the transition region is compressed, the focal region is enlarged, and the outside region is normal, okay? And you can implement this in a volume renderer, and okay, I have some pictures of this here. You know, this is essentially like this, right? So here is the regular lens, like there's just a round lens that I showed you here, right? This is the no lens at all. Here's the round lens, and the lens is here. And basically, what happened here, you basically expanded this lobster in a round way. So the lobster looks like it's pregnant in some way, right? It's already round, right? It doesn't really preserve. It basically took the not formerly very skinny shape and made it like round, right? Because the lens is round. And here the lens is square, so it made it even worse. Right now it has the lobster as like a square body now at this area. And here what I show, because as opposed to regular lenses like in physical space, I can make lenses that I can design on a computer, but they don't have a realistic counterpart, right? For example, I can design a lens where the boundary exactly maps to the boundary of the lobster, right? There's the boundary of I can expand it exactly in terms of the boundary of the object, right? And then I can get this. So basically here I designed a lens where the body is still square, just like long, like here. You know, there's no distortion of the body. It's just wider, you know, it's just wider. but it's not round, unnaturally distorted, or square, unnaturally distorted. Here it's naturally distorted in terms of the body's shape. It's just bigger now, but the same aspect ratios are there. The local aspect ratio is there. So that's just want to tell you that you can choose lenses. You know, you can now define lenses as you wish, right? You can just you can design a lens, then implement it like this, right? You design certain lens pattern in 2D or 3D, right? In 2D lens, take a lens, define compression regions, define transition regions, and just render the picture based on that, right? Based on that model, right? This is a paper we wrote a while ago with Lujin Wang, 2005, called the magic lens, magic volume lens. Then you can go one step further and you can stretch it even more, right? You can design this lens here. This is really basically an elephant. And what really happened was you go around an elephant with a line camera, right? And you walk around the elephant one line at a time and just take these lines and map them one by one on the side. And then just put them together like this. So now basically you have one picture that can show all the different views of an elephant, right? Looks a little funny because nobody sees elephants like this, but it's information visualization, right? Now you can really see the data from all different views at the same time, right? You know, it's not realistic, but it's informative. Here, this is by MC Escher, where this is like a very extreme form of lens. He basically moved the lens and blended them together. You know, this is like a single building, but he moved the camera all over the building, around the square yard and the courtyard and so on, and just stitched the views together in such a way that they sort of give a good overview over this building, right? So this is really done by hand, right? MC Escher, he did not have lenses like this. This is not a computer rendered. This is a man rendered, right? But it's a lens. You know, you can simulate on a computer if you want, right? So other lenses are these fisheye lenses, okay, for graphs, right? When you can send on any kind of node, right? You can say, this is my node, my center node, and everything else basically becomes children, right? So this is like center node here, and then whatever, you know, this is basically a regular tree or regular graph. It's just a graph, right? It's just a graph. And then take a node, and then all those nodes that are connected, all these subgraphs that are connected to the center node, are basically mapped to the surround, right? I can go anywhere I like, you know, I can go here and make that my center, and then everything else is mapped, right? I can any node can be the center, and everything else becomes displayed around it, right? So this is a really nice way to sort of investigate relationship of a particular node in a graph and see how it's related to everybody else, right? So it's a pretty nice, called the hyperbolic tree fisheye lens, right? It's pretty nice. It's pretty old lens, but it's really effective, right? A really good way to visualize graphs. Any node can be put in the center, and then all you have to do really is just to compute, you know, the angle of, you know, if you have like so many children, right? No matter how bushy they were, and you just map them around, make some space for them, right? So if this is bushier, then have to make more space. If this is less bushy and so on, right? So you have to plan the layout a little bit depending on how much is hit, how many children, or how much stuff, how many leaf nodes, or how bushy that tree is, that subtree is, you know, have to plan more, have to plan the space, but you can lay it out. You know, it's easily done, right? This is another one, table lens, where you look at certain graphs in more detail, certain areas more detail, and so on. So I want to stop now with this lecture because we're hitting the time where it's 80 minutes. And so we'll continue with this lecture next time, interaction. And next time we're also going to talk about dashboards, and dashboards is very important for your final project. You know, we're going to talk about this.